Hello and welcome to my class. I'm Grolin Annalisi from ThinkMo Education. I'm currently a Cisco Technology lecturer. If you like my video, welcome to my study group. Or contact my teaching assistant. WhatsApp account is +6 583444290. Today's topic is ACL, NAT, and SDN. We talked about some basic concepts of ACL in the last class. Actually, ACL is based on the current network status. When the communication has been completed, then go to do some corresponding control in a targeted manner. Then control access between some data. So let's talk about the experimental part of ACL now. Let's practice. Look at this picture. This is the experimental environment. The requirement is simple. PC1 cannot ping PC2. But today, I'm going to teach you some configuration commands that we haven't learned before. Everyone will find there is a PC1 on the left. It is on the 10.0 network segment. There is a PC2 on the right. It is on the 20.0 network segment. In short, both of them are across network segments. There must be a gateway in between. So here the gateway is introduced. Since there are two devices in the middle, definitely the device we're going to configure accordingly. First, I need to make sure the network can reach the device on the right. That is to say, these two devices need to run the corresponding routing protocol. Then let's configure them. Today our configuration is done on the device R1. That is, I hope that when PC1 goes to ping PC2 again, traffic sent. But it can't reach PC2. This is what we call access control. So we need to be on the left interface of the R1 device. Hook up the ACL. That is, configure the corresponding ACL policy on it. Then intercept the data under the interface. When I send data through this interface, after being matched by the interface, then we intercept the message that PC1 wants to ping PC2. It will not be forwarded by the router. In this case it will not be able to ping. This is what we want to achieve. Then let's see how to achieve. Before we realize the requirements, definitely have to do some basic configuration of them. We need to configure some basic addresses for PC1 and PC2. First is PC1. We directly configure the IP address 192.168.10.1. 24-bit mask. Gateway is 192.168.10.254. This is PC1. PC2 is 192.168.20.1. 24-bit mask. Gateway is 192.168.20.254. Okay. After configuration, we are going to run the corresponding routing protocol on the router. It starts slowly. We are still running OSPF. Although you will learn EIGRP in Cisco, including you will continue to learn in the future. But to be honest, it's really not used much in the network now. There are many application scenarios of EIGRP before, but not anymore in recent years. Or equipment. So let's see. We still run OSPF. First do some basic configuration. Let's name it first. A lot of content today revolves around experiments. By the way, everyone will also review the previous experiments. This is R1. The right device is the same. This is R2. Remember how to run OSPF? Before running, we have to configure the address for it first. E01 interface. This is interconnected with PC1. Its address is 192.168.10.254. It has to be the gateway of PC1. 24-bit mask. Then we go to the E00 interface. The address is 12.1.1.1. Then go to R2. R2 is the same. 00 interface. 12.1.1.2. Then the 01 interface. 192.168.20.254. OK. After we finish the basic configuration, start configuring OSPF. First configure a process ID. Suppose the process ID is 100. Router OSPF 100. We will not enter the router ID here today. We just declared. I teach you a new way of declaring. This way of declaring that we haven't talked about it before. But you can do this as an experiment. Definitely don't use this at work. 0.0.0.0. 0.0.0.0. Area is also 0. This is how we declared before. For example, there is a 192.168.10.1 on the left. Then I declare 10.0. Then R1 and R2 are interconnected here. I declare 12 network segments. Neighbors between them. After declaring the directly connected segment, pass routing information on both sides. Then we declare that 4 zeros are the full declaration. Full declaration. Declare all the interfaces on the current device. Look. All are 0. Mask is also 0. Full declaration. Once you enter this command, both interfaces of R1 are fully integrated into OSPF. Here is a simplified command. Sometimes you want to do some low-level configuration through OSPF. Then you can go for a full announcement. But if other experiments you do in the future will be related to the details in OSPF. For example, there are a lot of routing entries. Then you probably want OSPF to be more granular. Don't do it this way. But this can be used for your daily experiments. OK. Router OSPF 100. Then declare. Full declaration. When we declare done, we'll just wait here at R1 for a while. Let's check the routing table. It will be slightly slower. OK. It learned the route of PC2. We have to wait a while. So OSPF does have a bit of waiting time. This is learned in OSPF. The route of R1 to network segment 20 is this segment. It has learned. This is the OSPF we talked about earlier. We can then let PC1 go to ping PC2. First test their communication. Ping 192.168.20.1. It works now. PC1 is 10.1. PC2 is 20.1. OSPF is running in the middle. The two PCs are connected. Then I now hope that PC1 cannot ping PC2. Before we configure, we're going to review the ACL first. First of all, it must be configured according to actual needs. Now this is the need. Actually, we can do configuration anywhere. You can also try it after class. It is also okay to do it on the left interface of this device. But because the source IP of the layer 3 IP address will not change, including the peer service you visit will not change, you can do the same under this interface. Then we will configure it under the left interface of R1 today. I don't want it to ping right now. If I intercept this data, I mentioned ping. What can you think of? This ping we send must be a message. Then when I go to ping, I am sending an echo message. It is an ICMP message. It is divided into two. One is request. One is reply. Echo is request. Echo reply is reply. Actually, You can kill the request or you can kill the reply. But we usually kill the request. Because it's more crisp. Don't let this message pass. So we configure on R1. Now we have finished the basic configuration of R1. So now I'm going to enter the ACL on R1. We haven't talked about ACL configuration before. ACL is called access list. Let's enter a question mark to see. Here, as we said before. 1 is standard ACL. It is from 1 to 99. 1 is extended ACL. Is 100 to 199. Actually, there are relatively few scenarios where basic ACLs are used. As a basic ACL matches the source IP. For example, if you are now denying the source IP of a data. So now this source IP can't go anywhere. As long as this interface deny it. It cannot access all network segments and services in the rear. So, this is equivalent to directly limiting the overall communication capability of this address. Such lethality is too strong. So actually, we don't use a lot of basic ACLs. We actually use more advanced ACLs in our lives. For example, this is a server. I can do it. Can't ping this server. But you can remotely telnet to this server. We'll have a comprehensive exercise in a moment. I'm going to show you this part. That is, although PC1 cannot ping PC2, but it can log in remotely. So now the equivalent of just hope it doesn't ping. We call such a function ping ban. But PC1 accesses other services. Or provide it. So we cannot directly deny all traffic from PC1. Otherwise, PC1 can do nothing. We should use advanced ACL here. Its overall number is between 100 and 199. We will enter 100. Here is a deny and permit. Don't worry about the remaining two. We know these two at this stage. We must deny its traffic. Deny. Then you can see the message here. Various protocols. Then there is one of them called ICMP. We just want to deny its ICMP message. That is, deny one of its ping packets. After we enter ICMP, enter another question mark. Here is a source address. As source address, it can be a network segment. But you see there's a more precise one under it. A single source host. It's called the target host. I give a simple example. For this picture. Now PC1 is 10.1. If a switch is connected under this device now, the switch is connected to a 10.2 address here. Same network segment as PC1. If you are now on this interface of the router, deny such data from the entire network segment of 10.0. Then in the future when 10.2 goes to ping 20.1, it also can't ping. So often, our requirement is that PC1 cannot ping PC2. We will not target the entire network segment where PC1 is located. Use the entire network segment of the address. We don't do that. We often choose this host. That is, use a single exact host address. Since we want to limit PC1, just let it match the overall flow of PC1 precisely. Only affects it. In the future, if there is a device on the same network segment as PC1, they have nothing to do with ping PC2. So here we do intercept. Only for such a precise IP address. So we use host here. We need to configure the address of host A. 192.168.10.1. Then I will put a question mark. Here is a destination address. There is also a single destination host below. So we still hope that it can go to 192.168.20.1 alone. Mean the same. I just hope it can't ping PC2. In the future. If PC2 has a 20.2 on the same network segment, then PC1 is also allowed to ping through. So we minimize the range of lethality. Remember my words. When we are doing ACL in the future, what do you need? What kind of corresponding configuration do you make? Do not go beyond what is required. Okay. This is an exact address. Enter a question mark at the end. This is when we limit ICMP messages in the future. The following parameters you can configure. Let's find out which one is the parameter we want to use. It is this. Called echo. I hit enter. Then exit. We can look at the configuration of the ACL. Access list. I configured a 100 here. This is the high-level ACL of 100. It has a number of 10. Deny the echo message in the ICMP service. From host PC1 to host PC2. We specifically enter such an ACL. But you will find we seem to have not entered the previous 10. It is a serial number inside the ACL. You can also understand it as a number of ACL rules. Multiple rules can be defined in an ACL list. There is such a containment relationship between them. So what does this 10 mean? For example, I will now enter another access list 100. I add a deny ICMP to it here. This is optional. We do not currently have such an address. 192.168.10.2. Then the destination address is 192.168.20.2. Then we type an echo. I just typed 10.1 and 20.1. 10.2 and 20.2. Let's enter another one and see the phenomenon. This does not affect the configuration we will wait for. Deny ICMP host 192.168.10.3. Then enter a destination host. 192.168.20.3. After we have entered, check out the command just now. You will find. Now there are 2 more in the list. You will find that their overall order is. Starts with 10. Then 20. Then 30. This is called the step size of the entire rule. You can define your own rules. That is, you can define this serial number yourself. If we don't define this ordinal, it starts with 10 by default. And then accumulatively. 20. 30 and so on. So now you can see that there are so many matches in it. The first clause means it denies the ICMP message from 10.1 to 20.1. Its second article denied this again. The third deny this. What do you mean by this? I give an example. If we go to match. For example, there is an ICMP echo message from 10.1 to 20.1. It will be matched by the first. If there is a 10.2 going to 20.1 now, then it will compare. It will compare with the first one to see if it can match. Can't match. Because the source IP is different. Then it goes to match the second. Can't match. Because the destination IP is different. Then it goes to match the third. Can't match. Because the destination IP and source IP are different. If a data comes in Cisco, it does not match any of these 3 rules in all lists. Then we will discard this data packet. We will deny this data by default. That is to say, for Cisco, if we are doing ACL configuration, there is no corresponding matching item for some data in the ACL. Then after you call under the interface, Cisco will have a default command called deny any. That is, if for a data you did not deny or permit it, then it is deny by default. For example, now comes a 1.1 to 2.2. When you come here, you will deny by default. Because although it is not clearly stated that This is a default configuration. Sometimes, everyone go to other places to configure commands. You have to pay attention to this. That is to say, when we are configuring Cisco, there is a very critical order. You must know. What we just entered is access list 100. Then let's permit here. When I now permit, I enter a question mark to see. What I am doing now is the configuration of advanced ACL. Then inside I should go for the next parameter is IP. In the ACL, if you don't know what protocol you're matching, that is, no clear rules. Unlike the demand we are talking about today. Can't ping. Ping is an ICMP packet. You only know now. I don't want PC1 and PC2 to access. But there is no explicit access restriction. Then we use the IP. You can see that it is written after any Internet protocol. Now all these agreements you can see. In fact, they are all Internet protocols. Both belong to the protocol of the IP layer. Of course, some are higher. But I'm going to tell you. If you don't know what to type, you just enter the IP. It will match the service on all of these now. We enter the IP here. Later it writes source address. You need to let go. Or, how much traffic do you need to specify? How much to enter here? We want to allow traffic from any to any, which is equivalent to, in Cisco equipment. You finally finished configuring the ACL. To enter a command like this. Otherwise, as long as you don't make explicit data, all are deny. Then in the future, there will be a lot of internal hosts that will not be able to access the Internet. You must enter a command like this. Permit any. That is, all future traffic from anywhere to anywhere is allowed. I just deny the rules I just made in it. This last command must be remembered. It shows in the list. Is such a concept. That is to say, source is any. The purpose is also any. We allow all traffic. The whole list is now complete. I have sent ICMP request packets from PC1 to PC2. It's all denied. Now PC1 seems to be able to ping PC2. Because we are now only matching the parameters. And defines the matching action. The matching parameter is PC1 to PC2. The matching action is deny. But now there is no hooking under the interface. Then I told you. If you want the ACL to take effect in the future, you must mount it under the interface. Also called calling. Because in the end whether it is deny or permit, all need to be done through the interface. So we're going to start looking for interfaces now. 01 interface of R1. Let's take a look at the configuration. Interface E01. After entering this interface, we're going to enter a command that calls IP access group. We'll just put 100 here. After that here is a direction. There is an inbound inside. And an outbound. They are packets in the incoming direction and packets in the outgoing direction. We enter in here and it's okay. After typing, let's use PC1 to ping. Or this command. Let's go to ping 20.1 again. It doesn't work. And not only. It also shows these here. It means now it is denied through some behaviors configured by the administrator. It is an unusual communication situation. This is before being denied by the administrator. This is normal communication. Now this is a communication denied by us. So above this is what we are talking about advanced ACL. Next, let's briefly talk about the basic ACL configuration method. Let me demonstrate the configuration command. I won't give you an example for the scene. For the back. Because the number I entered is 10. Then it is a basic ACL. Everyone can see. I enter permit in the back. We can do some configuration. Then let me show you. This is the host. This is any. Let's not talk about it. Let's talk about this segment. For example, I have entered the 192.168.10.0 network segment here. I can enter a 24-bit mask here. But we can enter a question mark before entering. You will find there is a thing called wildcard bits. This is a wildcard. We mentioned wildcards when we talked about OSPF. EIGRP and OSPF use anti-masking. Subnet mask is called positive mask. But in addition to the subnet mask and the reverse mask, when we make the announcement, we also have a close one called wildcard. I enter a bar 24 here. After entering this command, show access list 10, you will find I released a 10.0 network segment here. Then it writes a wildcard 0.0.0.255. You see, although I input a bar 24 forward, but it writes 0.0.0.255. Let me give you another example to explain what this means. In fact, for the current wildcard scenarios only in the first contact in the ACL, you will have more understanding in the future. When you get in touch with each other slowly. We are just talking today. For example, I enter another command. Access list 10 permit. 192.168.1.0. 0.0.0.254. Then I enter another command. 0.0.254.0. You'll find I can still type in. Let's check. I have now entered 3. This is the basic ACL configuration mode, followed by wildcards. Let's see. The first is 0.0.0.255. The second is 0.0.0.254. The third is 0.0.254.0. This looks weird. Let's talk about this. Because we actually use less basic ACLs. So wildcards are more worth talking about. Let's talk about this. First for the mask. Mask is the 24-bit mask we say every day. A configuration where we assign addresses to interfaces. 3, 255 and 10. It is made up of consecutive 1s and 0s. And it must be 1 first. Then 0 after. Cannot be preceded by 0. Because 1 means an exact match. An IP address plus a subnet mask can specify a network segment. Then the subnet mask is 1 is the network bit. A subnet mask of 0 is the host bit. It is mutable. All the network bits we stipulated are filled with 0. This is the address of a network segment. So the mask must be consecutive. Can't be out of order. Continuous means it has to be 11110000 instead of 110101. Then the anti-mask we said before is turn this 0 into a 1 based on the mask. Then turn 1 into 0. Just like we talked about the OSPF announcement earlier. The original 24-bit mask declares a network segment. Should be 24-1. Then 8 zeros. When we declared it was 24 zeros and 8 1s. Its anti-mask is composed of consecutive 0 and 1. And 0 and 1 cannot be out of order. Must be preceded by 0. 1 after. This is called anti-masking. Then, for the anti-mask. It is actually such a relationship with the positive mask. Exactly the opposite. So what will use the anti-mask? Just like OSPF and EIGRP. All anti-masks are used. We're talking about wildcards today. Wildcards are the only thing we will touch this concept in ACL in the NA phase. Called wildcards. We call it the jump mask. Pay attention to my words. It is composed of discontinuous 1 and 0. And it is for us. 1 is random. 0 is an exact match. 1 in the mask is an exact match. 0 in the anti-mask is an exact match. Then 0 in the wildcard is an exact match. This might sound a little difficult to understand. The latter two as examples. The first one is too regular, so don't look at it. Let's calculate the two harder. First look at 192.168.1.0. Its wildcard is 0.0.0.254. 0 means it is an exact match. This 0 means that the first 8 bits are all 0. The first 8 digits represent 192. It is fixed. Let's just say. In fact, we don't need to be so clear about the realization stage. But you have to understand. Now the first 3 digits are all 0. Represents 192.168.1. This is an exact match. Then the next bit is 0. It's actually 8 zeros. 0 0 0 0 0 0 0 0. This 254 is 255 minus 1. The last of these 8 bits is 1. So 254 should be 1111110. Now corresponds to this bit of 0. Represents an exact match. The first 7 digits represent any. The last 0 is an exact match. So when we calculate, let's see what changes these 7 can bring. Let's say a few simple. Here side can be written as 00000010. 0 is the last digit. Is precise. This bit can become 1. Then I add 1 up. Becomes 00000100. Further down it becomes 00000110. The last digit is fixed to 0. This bit actually changes between 0 and 1. Actually, at the beginning, this bit can be 0. To us. If it is 0, represents 0. If here is 1, represents 2. If the previous digit is 1, represents 4. If these 2 bits are 1, it represents 6. So, if you write wildcards like this, what it actually matches is from 192.168.1.0. All even numbers up to 192.168.1.255. It matches actually all even numbers. Because for the entire 8-bit binary, 128 from the first, 64, 32, 16, 8, 4, 2, 1. Only the last digit is odd. So if the last bit is fixed to 0, then it means that, no matter how the previous numbers are combined, it is impossible to calculate an odd number. It is always even. So if we use the last digit is 254, then it represents, in this range, you will match all even numbers. As the name suggests. If I change the last bit to 1 here, then you will match all the odd numbers here. Because this one will always take the value. No matter how the above even numbers take value. Just add an odd number at the end. It's an odd number. In fact, it is not very useful at this stage. But in the future when you learn protocols like BGP, you'll see wildcards again. So now let's just understand. Let's briefly talk about this 254. For 254. The last one it is 1.0. After 1.0 this is a 254. It means that here are 7 ones and 1 0. Then the rear is a 0. Then below this is 0. Represents that the last digit is fixed. Only this is a 254. The last bit in 254 is 0. Then it is actually 0001. So when we go to match, it is equivalent to matching all even numbers in this interval. Look at the 254 just now. It's just the last one. Now this 254 is placed in the middle. This is a 1. Is 00000001. It is 11111110. Represents that except the last one is 1. Everything else is arbitrary. I also said, it will match all odd numbers in the interval in this range. Because the last bit has a value of 1. No matter how you add it to the front. The front is mutable. No matter how it changes. It is an odd number. It is equivalent to if we use this form. 192.168.1.0. Its wildcard is like this. It is equivalent to this 192.168.x.0 that it matches. X is any number. That is, all odd-numbered network segments. For example, 192.168.1.0, 3.0, 5.0, 7.0 etc. So we call the wildcard a jumping inverse mask. You may find it difficult to listen. You can watch the video several times after class. You need to know what it means. Here's what we're talking about: masks and wildcards. Actually, our ACL is finished. If for basic ACL configuration, you want to match the previous network segment, dedicated to killing a network segment, you can try to configure it yourself after class. The command is like this. Enter a matching IP address. Add a wildcard after the IP address. Usually, if it is a 24-bit network segment, followed by 30 and a 255 on the line, under the adaptation range of a relatively regular network segment. It actually looks the same as the anti-mask. Unless you have special needs in the future, you have to use wildcards again to calculate. At this stage, you can understand it as an anti-mask. Okay. Above this is the ACL. Let's talk about the next experiment. We are going to learn NAT. For NAT, we will configure while teaching. I turn it off first. Let's start the next experiment. I have to open it first. Otherwise, it will be a little slow to load in a while. This is an experiment with NAT. Like ACL and NAT. Actually, they are very simple. It's for experimentation. First, let's talk about the NAT scenario. So let's discuss a question. It is known. The address we are using now is an IPv4 address. Now the overall network environment uses IPv4. Remember how many IPv4 addresses there are in the world? When we talked about IP addresses before. A total of 32 bits. Each bit has two values 0 and 1. That is 2 to the 32nd power. About 4.29 billion addresses. Less than 4.3 billion. The world now communicates using IP addresses. As long as the device wants to connect to the internet, must have an address. That is, now all devices that can be controlled through the network, it will have an IP address. For the world, 4.3 billion addresses are not enough. We said it before. We will use private network addresses internally, and run the public network address on the public network. Then everyone will have heard a sentence. The private network address cannot run on the public network. The public network does not forward the traffic of the private network IP address. Why doesn't it forward it? For example, 192.168. This is a standard C-class private address range. An address like this, since it is a private address, it means that we can use, whether at work or at home, even a small restaurant outside, for such an address that everyone can use. If someone sends a data in the future, go to 192.168.1.1. The data reaches the carrier's device. If it can really help you retweet. So where is this address? For the whole world. Use an address segment like 192. So many private addresses. It does not know which 1.1 you are going to. So it will not help you with data forwarding. That is, because the addresses of these hosts in our internal private network has too much overlap. So when the operator forwards, it will appear confusing. So it can't help you retweet, since it can't be forwarded. How do I get online now? We are now deploying a technology on export called NAT, Network Address Translation. It is possible to convert between addresses. That is, when we are sending data, we're going to convert the data to it. We modify the original address of the data. Then we can convert the private network address into a public network address. Form a local mapping information. Then I can send data. Then if the future data is returned, when I receive data, will be based on the current destination address in this local mapping information table, to see if there is this record. If so, then we convert the address back to, that is, change this destination address to a source IP of the private network in the NAT table. This is the idea of NAT. Modify the source address of the data when sending. Change to a public network address. Form a message locally and send it out. When receiving data in the future, send it to this public address. Then I check in the local mapping table. Is there a private network address converted to this public network just now? If there is, I will change the current destination address to the original source IP address of this private network. Send this data again. It might be more abstract. Let's look directly at this picture. This is a public network. Here is a 200 network segment. This is a public address. We use a private network address internally. In the future, when host A is surfing the internet, I would pass such a device here. When the data is sent out, a mapping relationship will be formed locally. For example, 192.168.1.1. It is now mapped to 200.10.10.1. Let's say this is its address. So now after forming the mapping relationship, this data will be sent out. This is the source IP. When a server on the public network receives reply packet to data, reply packet words, swap source IP and destination IP, it replies to this public address. Then this data will be replied to this interface of this device. Since this data is not sent by this router, it has to be viewed locally. Did someone just go online with such an address? If so, let's see who uses it. Is 192.168.1.1 used? Then the original destination IP in this data is 200. Is its interface. It now modifies the destination IP. Then send back. So equivalent to. Host A uses a private network to communicate with a public network. So this is how we go online now. NAT is generally deployed on a network connected to the internet. This is a base location where we deploy. There are 4 modes in NAT. Let's talk one by one. Make a configuration for each talk. The amount of configuration is still quite large. Let's take a look. The first is static NAT. When we configure, there are many ways to implement NAT. Static NAT is one-to-one between private network address and public network address. 1-to-1 is. I have several hosts with private IP. There must be several public network IP addresses for it to map. Do you think this method is useful? You said that a private network IP is converted to a public network IP. Then communicate with a public network. Another private network. You have to use another public network address to communicate with the public network. Then why don't I directly use this public network address to communicate with the public network? This is static NAT. Of course. Static NAT also has some security risks. But let's not talk so much. Because now it's useless. Let's just talk about how it's done. As a static NAT. This is a translation source address. Now host A sends a data to send to host C on the public network. This is the source IP and destination IP. Then after doing static NAT on the gateway, it will forward a corresponding. Then when retweeting, everyone will find the destination IP is unchanged. The destination IP is still this host C. That is the address. But the source IP was changed to 200.10.10.1. This is a public network. Internal future host B wants to go online. Then this 192.168.1.2 needs to access host C on the public network. The destination address remains the same. But here we need to consume another public network address. This is for 10.2. These are the two public IPs. It is equivalent to the current 10.2 mapped from 1.2 to the public network inside the host. Then go to communicate with host C. Then host C will reply the data packet in the future. It must be replying to the destination IP sent on 200.10.10.1. The purpose must be 200.10.10.1. It will now reply to 200.10.10.1. Source is itself. After the packet comes back on this device, just had a map entry like this. Converted from 192.168.1.1 and this 200.10.10.1. So it will now change the destination IP to the IP of my host A. Then send it back to host A. This is also the same. Actually, static NAT is a binding relationship. That is, we need to artificially make a binding. It feels the same as configuring static routing. We're going to do a static binding. Put such a public network address. The only one tied to this private network address. Only for it to use. The advantage of this is, I only need to go online in the future. You must be able to take this public network address. But the downside is that once I do the static NAT binding, for example, now I put this address of 200.10.10.1. Bind to this 192.168.1.1. Then even if 192.168.1.1 does not go online in the future, this address cannot be used by others. It does not have the concept of an address release. It will not be released. It doesn't. No one else can use it. Let's see what this static means. We do a basic configuration. When we configure, first of all, the equipment must be changed. These two PCs are simulated by routers. Because we will talk about a server on the internet later. So use a router. I'm done naming. But I don't remember how many configurations I made. I have already configured the address. Show interface brief. Okay. I did configure the addresses. Because today's class time is quite tight, I have configured the address. After I finish this, save this configuration first. Then let's start. How do we take a router to emulate a PC? I don't do other configuration now. Just configure an address for it. It is okay to use a router to simulate a PC. Then we have to turn off the routing function of this router first. No IP routing. We turn off its routing function. Secondly, we configure a default gateway for it. 192.168.1.1 is the address of this interface. I will write it. This is the current gateway. I put it here. This is the gateway interface. 192.168.1.1. Two PCs are on the same network segment. That's it. Then type write. You can save this configuration. We will use this configuration again and again later. So I just saved. Just to show you guys the command. I also enter no IP routing here. IP default gateway. 192.168.1.1. Manually configure the gateway. It's like a PC. I manually configured a gateway for the PC. The address is configured for the PC interface. Turn off its routing function. It's a PC now. As a router, you turned off its routing function. Then it is no longer a router. It's a PC. I configure a gateway for it. In the future, it will go to the gateway across network segments. So it really is a PC now. But we can configure some commands for it here. For example, I can let it be managed remotely. We just facilitate future configuration. So let's take a router simulation here. This is the basic configuration of two PCs. What I want to achieve now is, I hope this PC1 can access the internet. If PC1 can access the internet, we only speak from the point of view of configuration. How should we configure it? PC1 is now across network segments. Find gateways across network segments. Then the gateway only needs to have a route to 8.8. Since this is the operator, often the exit is a default pointing outward. Logically speaking, this address on the public network will not reply packets to the private network. We have a plan. From a configuration point of view only. Of course I can write a link here to 192.168.1.0. Dump traffic to the gateway. Gateway is directly connected. Just send it here. But what we're talking about today is, we want to access the extranet. For the public network, it will not write a static point to the internal private address segment. We cannot perform corresponding routing configuration on this device today. We are going to implement PC1 internet access. And the ISP passes it back. Which is equivalent to, there is no route to 192.168.1.0 in it. Then it needs to communicate with PC1 through other means. First send the traffic to the gateway. This is our need. Let PC1 go online first. We are also like this in reality. The gateway must first have a static route pointing to the operator. The operator will not have a static point to our. But we want the route to point to it. IP route 0.0.0.0. 0.0.0.0.0. The next hop is 100.1.1.2. After pointing out, the data can go out anyway. But does the data come back? We have to do static NAT on the gateway. Let's take a look. Let's open this first now. After opening, let's ping the PC first. Can you guess if this data packet from the PC can be sent out? I visit this 8.8. I have already configured the address in the operator. Can I get the data packets sent by PC1 under this interface? Let's ping here. Ping 8.8.8.8. First of all, we don't care if it works or not. Can I get the packet? Let's take a look. Now the data seems to be out. Did you discover it? We get the packets here at the operator. The packets I get under this interface. The obtained data packets can be clearly seen. Now there is a 110 sending data to 8.8. But 8.8 didn't return it. So it doesn't work now. That is, when the data goes out now. Since it is a private network address, there is no private network route on the public network. So it can't communicate. We have to configure it to come back. Do NAT on the gateway. We make a static binding for it. So the premise we are doing this must be: make sure the gateway and PC are able to communicate. It must work. Because the packets are out. So we are now doing static NAT mapping. In Cisco, no matter what kind of NAT you do, there is a command that must be entered. IP NAT inside source. No matter what NAT configuration you do, this command is necessary. This is a fixed configuration. We now do static configuration. I enter a question mark. There are 3 types. We use this static today. The route map is called the strategy level. UNP will learn it. This list we'll see later. Let's look at this static first. Enter a question mark after. Inside local IP address will appear here. That is, now you can enter whoever you want to access the internet. I want this 192.168.1.10 to go online now. I just type 1.10. Enter another question mark. Then, inside global IP address appeared again. For example, the network segment that is now connected to the operator is the 100.1.1.0 network segment. Suppose I have an address 100.1.1.3. Assuming this address is what I bought from the carrier. This address must be directly connected to the operator. Must be in a network segment. Otherwise, there is no way to use it directly. We can't just make up this one. Because this address is not given to you by the operator. If you configure this externally, over there is not acceptable. So, the public network address is not something we can use casually. If you use it indiscriminately, no one will use PPPoE. We also don't have so much technology. Everyone can use whatever they want. Then it is no different from private network. Addresses running on the public network cannot conflict. 100.1.1.3. I hit enter. I have now entered a static NAT. I mapped the internal 1.10 to the external address I bought. 100.1.1.3. And in a static way. But the configuration of light input is not enough. Cisco is more troublesome. In Cisco, you have to specify the internal network interface. An external network interface. Now the data flow is like this. PC1 sends data. Come in from this interface of the gateway. Then go out from this interface of the gateway. Then this interface will be an external network interface for you to do NAT. This interface will be an internal network interface for you to do NAT. So you need to be under these 2 interfaces respectively. Indicates that they are the interfaces used in NAT. So we now first enter this E00 interface. IP NAT outside. This is my external network interface for NAT. After we enter this command, it will be stuck for a while. Wait a minute. Anyway, this command will get stuck every time it is entered here. So don't think it's a problem with your own equipment. Now 00 is outside. 01 is inside. That is, when you do address translation, which is the internal network interface? And which is the external network interface? That's what I mean. Okay. Then enter the 01 interface. IP NAT inside. And we're back now. To view the mapping table. Show IP NAT translation. Now this is called NAT mapping table. In the table it says inside local. That is an internal private network address. This is 192.168.1.10. Maps to this external 100.1.1.3 here. Then we describe the process. PC1 wants to go online now. It accesses 8.8.8.8. Cross-network segment. Find gateways across network segments. The data is sent to the gateway here. Since this interface is the internal network interface of NAT. After checking this data, if you go to 8 now, need to go out from this external network interface again. So at this point it will start NAT. Because it also happens to be 1.10 now. After the data comes in, the gateway knows that it was sent by PC1. PC1 wants to go online. Then this static NAT will take effect. So the start of NAT needs 3 conditions. First, must come in from the internal network interface. Second, must go out from the external network interface. Third, there must be this corresponding representation in the NAT table. Data to go out. Then once the data is now out, can you guess PC1 can ping 8.8 now? Let's verify. 8.8.8.8. When pinging, we get a packet here. I'll put a mark here first. Wait a minute to see what message is sent if it is connected. Look. Here's a dot and 4 exclamation points. This proves it works. After we pass, we will suspend. Let's take a look at this message. It didn't work. Originally, this packet was sent from 192.168.1.10 to 8.8. Now this is sent from 100.1.1.3 to 8.8. So you see that 8 replied to 100.1.1.3 with a packet. Because 8.8 is a device of the operator. It has a route about 100.1.1.3 on the device. That is the 1.0 network segment. Because it is directly connected. So it has such a route. With routing it can reply packets. Original no reply packet. It is because it does not have the route of the private network IP. So no reply packet. Then you will find. Now the source address has been modified. Changed to public address. Let's do a simple demo. I'll talk about other things later. I won't get data packets for everyone. Time is tight. If you are interested, you can try it yourself after class. Now the entire Ethernet communication must use ARP. It's a stipulation of the agreement itself. Okay. We just finished talking about static NAT. Let's talk about something else. We are now online normally. After going online normally, we can look at a parameter on the host just now. Show IP NAT. Let's take a look at the mapping table just now. This is a static mapping. Mapping from an internal address to an external address. In fact, static NAT is a two-way mapping. That is, whether from the inside out or the outside in. It is all mappable. So, as a static NAT, even if internal hosts do not access the internet, once it is bound to the address of the external network, then this public network address cannot be used by others. So it's very unoptimized. So can we optimize static NAT now? For example, now when I am doing data access, if I want to use this address, I will take it and use it. If you do not use this address, I'll return it for someone else to use. It's okay too. We have a method called dynamic NAT. But whether static or dynamic, we don't use this much. So let's take a brief look at its configuration. Don't need to do too much research on it. We don't use it in real life. Because as a dynamic NAT, it will also have a release time. That is, It still defines the pool here. When we talked about DHCP before, actually defined this thing. Address pool. The public network also needs to define a public network address pool. You will find that there are still 2 public network addresses inside. Of course, there may be more in the future. Then it means host A finds an address when surfing the internet. Host B finds an address when surfing the internet. If the future is not online, return this address to the address pool. For example, in the future, host C wants to communicate. It can take the address and use it. It is compared to static NAT. The advantage is, when I use it, it is actually a private network occupying a public network. It's just that the difference is, if I don't use it, I will return this address for someone else to use. But this method still requires a lot of public network addresses. Otherwise, when the internet host is online, they are still all facing one traffic at the same time. Concurrent traffic. If it's still like every day, host A goes online. Host B goes online after a few minutes. In this case, one address is enough. But in real life it is often impossible. I want to go online. We have to wait for the previous person to release the address first. Then I go online. This doesn't happen in our daily life. Even in such a way, it can recycle addresses and reuse them. But for the high concurrency traffic in the current network, it is far from meeting our current configuration requirements. We won't use it in practice. So let's configure it. We mainly look at its configuration direction. No matter what kind of NAT, both the network ingress port and the network egress port need to be configured. The ingress and egress ports are the 2 interfaces 00 interface and 01 interface. We should have configured. Actually, we call dynamic NAT many-to-one, or many-to-many, multiple internal private network addresses to multiple external public network addresses. We dynamically make an allocation. And for NAT, it needs to be used in conjunction with ACL. ACL and NAT can be used in combination. Like static NAT. You don't need to use it in combination. By default, if this ACL does not define, then it is assumed that we have not obtained any data. NAT will only convert the matching data for ACL. That is, what data is obtained by ACL? What data is converted by NAT? If you don't write any rules, the default is not to do NAT translation for any address. It must be converted when it is combined. If it doesn't match now, don't convert. So I can't get online. So wait a minute while we configure. We also need to configure the ACL. This is one of its configuration specifications. For ACL, use ACL alone. Just one of the methods. When we were configuring the ACL just now, you should see the route map there. ACL can be used in combination with many other directions. Actually, it can be used alone, and there are also scenes. But it is used in more scenarios in combination with other directions. And when using, the meaning is not the same as using it alone. For example, if I want to make an ACL now, I want them both to be online. I will define 2 addresses here later. Let both hosts go online at the same time. Now if I want to match the traffic of the 2 of them, should I use a basic ACL or an advanced ACL? For example, now I want it to access 8.8. But for us as everyday users, I want to go online. Whether it is 8.8 or 9.9 or 10.10. No matter how much. Internally there are now 2 hosts. But there may be a dozen in the future. 20. Or 30 hosts. I can't do an exact match. It cannot be said that if you do route broadband, you only let it access this 8.8. Access to 7.7 does not work. Can you make a limit to its purpose? Including the future to limit it to a port. For example, only let it access port 80 of 8.8. What if it does not open this port? For the internet, we act freely. Can do anything. So now you just need obtain the traffic of the host users who belong to the internet and want to go online. Just let it out. So we use the basic ACL on the line. Then we start to configure. We need to do the corresponding configuration on the gateway. Access list. Let's just enter a 10. Permit any. Let's let all the hosts below go online. In fact, you can also enter 192.168.1.0 here. 0.0.0.255. This is okay. So now it's just a matter of grabbing this traffic. As long as you configure ACL, ACL can get these traffic. So, get them online. Please pay attention. For this permit, if ACL is used alone, permit means to allow. And when this permit is used in NAT, it means grab. For the experiment we just did, means the data comes in. Whether to allow normal traffic forwarding now. It is an allowed concept. But here it means fetch. That is, match the data. In the future, as long as ACL is combined with other directions, e.g. policy routing, when combined with them, permit means to grab. It is used to capture traffic. The specific execution actions and strategies are completed by other tools, rather than being done by the ACL itself. So its binding ability is very strong. It's more like an extensible tool. Combine with anything. Now the intranet host has done this. We will make an address on the public network later. IP NAT. We are here to define a public network address pool. Call it NAT. Let's type a question mark to see what it is. There is a start IP address here. Let's assume that starting from 100.1.1.3. Enter another question mark. Let's assume end from 100.1.1.4. I give it 2 addresses. There is going to be a mask here. Mask is 24 bits. I have now created an address pool. There are 2 public addresses in the address pool. Start and end. If this input point 5 is 3 addresses. I just configured an ACL. This ACL is used to match the addresses of these devices that can access the internet. Then I will now have multiple hosts on the internet. Match multiple addresses on the internet. I'm going to combine them. Remember that basic command we just had? IP NAT inside the source. This command is what you must enter no matter what configuration. List 10. It is the 10 we just defined. Pool NAT. This NAT is the definition we just made. This is an address fixed format. List 10. This is the multiple PCs we just grabbed. Pool is our public network address. So we now put these PCs inside. Map to this external public network address pool. Let's ask these 2 PCs to ping. Ping 8.8.8.8. This PC also goes to ping. Ping 8.8.8.8. Now both of them can go online. Because they now have multiple public addresses. We don't actually use it much at work. If you're interested, let's get to know each other privately. We mainly look at the configuration. Okay. Now I'm going to reboot the device. Let's do the most used command now. This is the most important. We just defined too many things. So now need to reboot. We do not need to do any configuration on this switch today. We open it. Now let's talk about the last mode of NAT. The last one is the one we use most now, called PAT. P means port. We now use more port conversion. That is, port and address translation. There is still a circle. But this circle is different from what I just wrote. There is only one address in this circle. It has only one 200.10.10.1. But it corresponds to a different port. And this picture is like this. This is a 10.1. This is a 10.2. Here are two addresses. This PAT is an address. But the difference behind is the port. For the form of PAT, network address port translation is allowed. Multiple internal private network addresses now. Different ports map to the same public network address. This is a concept of it. Allow mapping like this. This is what we use now. An external public network address. Multiple internal hosts use one address, but using a different port. That is, modify both the address and the port. Because for the port, its overall range of variation will be greater. I said before, there are 65,535 ports in total. Let me tell you about the number of ports. That is to say, we actually use this form now, whether at home or at work. In fact, this is the way. Multiple hosts. Address and port conversion at the same time. So let's take a look at how it communicates now. Now internal host A is 1.1. When it visits host C in the future, it will have a local random high port, greater than 1024. For us now, it locally takes its own address plus a high port. Go to port 80 of 100.1.1.1. Prove that it is accessing its HTTP service. When it is accessing, there will be a public network address at the exit. 200.10.10.1. When the data goes out, it will send port 1025 originally from the address 192.168.1.1. Convert to port 2843 of such a public network address. Then the destination IP and port remain unchanged. Sent to host C. After the host receives it here, swap source IP and destination IP. Swap source port and destination port. Reply traffic to port 2843 of such an address. When the device now receives the data from the public network, when it accesses the local port 2843, then it checks the mapping table just converted. It will convert this data back to port 1025 of 192.168.1.1, which is equivalent to the variables in it except the address. Actually added the port. Then you will find, due to different ports, we can then distinguish traffic from different PCs. Even if the internal host B generates the port starting with 1025. No problem. Because the ports that may be generated by the two hosts are the same. But when the future is converted, the external port will never be the same. Because there will be some port records on the device. Will be stored in the mapping table. Now this port has been used for port 1025 of internal host A. Then in the future other devices want to go online. Also use its address. But with its different port. When we record in the device, is to take the address plus port. Map address plus port. As long as this variable is different, we can uniquely locate such a data. And then convert. Equivalent to a larger convertible space. So it saves our IP address even more. There are two methods we most commonly use now. It can also define a public network address pool. For example, I can also have 10.1, 10.2, 10.3 etc. This is also possible. In the address pool, data sent by hosts. First take the first address and different port. First run out. Make a second one. The second is exhausted. get a third. You may ask, how can it be possible to run out of 65,535 ports? Generally speaking, there are about 100 people in the company. Almost can exhaust so many ports of an address. You should know. A port is not a device that only generates one mapping. Now the same device has many programs open. For example, listening to music, watch a movie, playing games. Now overall, a device may have dozens of processes accessing public network services at the same time. It consumes dozens of ports for accessing the public network. How do we judge the mapping? As long as the device wants to access the public network address, plus port is different. It will have a piece of data out. When the data is sent out, a mapping will be generated. Therefore, our daily internet consumption consumes a lot of ports. For enterprises, it's almost the 100 people I told you. Basically, a public IP port is almost used. Of course, if there is not much demand for internal internet traffic access, you may find that 200 or 300 people are enough. But if your daily demands are too high, about 100 people are almost exhausted. So sometimes we will define the public network address pool. But for the vast majority of small and medium-sized companies, none of us do it this way. Because the public network address has to be bought. It still has a cost problem. So what we use most now is, although there is no public network address pool, but it has a public network address. The outbound interface that RA is now connected to the operator is a public network address. Then I will no longer define the public network address pool. I just use this interface for conversion. For example, this is the address of the interface. Future traffic will be based on this interface. Then just do it on a different port. I don't need to spend any more money. It is 10.1. Let's say it's 10.2. I still have to pay for a 10.3. Then map the address and port to it. Don't do this. I just use this 10.1. This is a public address. In Cisco, we call this method the conversion of the outgoing interface. And this command is bound under the outgoing interface. The outgoing interface address can be changed. To use the changed, it does not matter how. The address of the external network interface changes. So now for many companies, how we use the internet. Not a fixed IP. We use the form of PPPoE. Every time I dial up, the obtained public IP may be different. But this does not affect us to do NAT. Because we can use the public network interface. Do the corresponding NAT conversion. Then the interface of the device is 1.1.1.1. I just use the 1.1 port. The interface of the device is 2.2.2.2. It dials up to get a new address. I just use its interface. Because this command is bound to this interface, rather than a fixed address. So it doesn't matter how the interface changes. Let's demonstrate. The device is now rebooted. These should all be empty configurations. No. Not an empty configuration. I have configured the address. Then let's look directly at the configuration. The full name of PAT is Port Address Translation. I first check if the command just now is saved. Show run. OK. I just turned off the router. The PC should be all set up. After setting up the PC, we are now going to configure a default route for this gateway. IP route 0.0.0.0. 0.0.0.0. The next hop is 100.1.1.2. After we enter this default route, still need to configure ACL. Access list 10. We still use the same traffic as before for crawling. or to allow the two internal PCs to access the Internet. We match 192.168.1.0 this time. 0.0.0.255. It was any just now. We now match the 1.0 segment, plus a wildcard. Then press enter. We're done now. It is equivalent to getting multiple internal IP addresses. Now I'm going to map it to an external interface. IP NAT inside source. This is constant. Then I still associate it with list 10. I enter a question mark. What we just entered is pool. Defines a starting interval to an ending interval. We now use interface. I hope that the traffic will be converted to this 00 in the future. The address of this 100. 1.1.1. I want to use it. Ethernet 00. Then enter the last command. Overload. Port multiplexing. That is, after the port is used for you, it can be released and used by others. We understand now. Port multiplexing. Press enter. Then when we press enter, there is another one we haven't configured yet. Remember the 3 steps I said? After first getting this traffic, you have to convert. But there are 2 key. We at Cisco must remember. Under the interface, make sure it is an external network interface and an internal network interface. Traffic must come in from the internal network interface. Go out from the external network interface. Then match the corresponding conversion. It can be NAT. Our 2 interfaces are not set. We also need to set interface E01. Get in here. IP NAT inside. Still have to wait here. Here whether you enter inside first or outside first. Need to wait a long time. This is a habit of its overall configuration. Probably for this order. The device is a little slow to process. But you enter the second command very quickly. Maybe there is something wrong with my mirror. I haven't seen this before on a real machine. Interface E00. IP NAT outside. We are now set. After setting, it is equivalent to. Now go to ping the 2 PCs. See if it works. Ping 8.8.8.8. Same here on PC 2. Ping 8.8.8.8. Let's get ready. Make them both a little bit at the same time. Okay. Let's see. Both work. You will find the commands we configure are different, but does not affect their communication. Show IP NAT translation. Here is our mapping table. Now you will see the contents of the mapping table. Inside local. Here are the 2 addresses inside. 2 addresses carry 2 ports. But ICMP does not belong to layer 4. ICMP is a layer 3 protocol. It is encapsulated on top of the IP layer. But it seems that there is no concept of port in it. ICMP has no port. So for some of these services without port, it is followed by a serial number. If you access other ports in the future, it is a port. But for ICMP, this is a serial number. Just know it. You can think of it as a port. Doesn't matter. 1.10. 1.20. You will find both PCs internally. The numbers behind them are the same. But it doesn't affect 2 people surfing the internet. This is what I just told you. We only need to have different port numbers of their outgoing interfaces mapped to the public network. For example, I am now going to get the internal address plus port. Map to external public network address plus port. Visit out. Future data will return to port 1 of this 100.1.1.1. Port 1 will be uniquely positioned to 1.20. So, it does not matter. whether the ports of the two internal addresses conflict or are consistent. Because the outside is different, we find the internet address based on the difference from the outside. So it definitely returns exactly. So it works. Doesn't matter if it's the same inside. It doesn't matter if you repeat. We are looking outside.